Hey, welcome back. So we're moving on to the third of our elementary sorting algorithms, the last one for this section, before we move on to some of the scarier ones, some of the fancier ones. Let's call it fancy instead of scary. So insertion sort, actually, it's pretty similar to bubble sort and to selection sort. We grouped them all together. However, there are a couple of key distinctions, some things that insertion sort is actually good at. So this isn't one that's just good to know about. It's not just a good challenge. There are situations where insertion sort does well, and I'll explain that as we go. But first, let's talk about how it works. So it builds up the sort by gradually creating a larger half of the array, which is always sorted. So instead of finding like the largest element at a time or finding the smallest element at a time, it takes each element and places it where it should go in the sorted half. So let's take a look. That doesn't really mean much, but if this is our initial state, we start with this. Our sorted half of the array is shown in green. So right now, half is not the right term, by the way, the sorted portion of the array. And our value we're looking at is 3. So where would we put 3 in order to sort this part? Well, we'd put it before 5, right? We insert it into the right place. Now we hit 4. Where does 4 go? We insert it between the 2. So now this is our sorted portion. Then we hit 1. Where should we put that? At the beginning. And we hit 2. Where do we insert that? Right there, index of 1. So you can see what happens is that we gradually build up the sorted portion of the array by inserting one item at a time in the correct place. So here's a quick walkthrough of it. If we start with this small array, we have 3, and we take 44, and we figure out where it should go in our sorted portion. Well, actually, it just goes right back where it was because it's greater than 3. That's where it belongs. But now we get to 38. Where should we put 38 in this left portion? We put it between the 2, like that. Then 5. Where should that go? Well, it doesn't go there, does it? Nope. So we have to check the next one. Does it go there? Yes. In between the 2. 47. Compare it to 44. Oh, you just go right where you are. 15. Compare it to 47. Nope. Compare it to 44. No. Compare it to 38. No. Compare it to 5. Yes. And now we have the sorted array. So hopefully you can see why it's called insertion sort. We are taking an element one at a time and inserting it in the correct spot. So as far as the pseudocode, what you do, you start by picking the second element in the array because our sorted portion will be considered the first element at the very beginning. So we don't need to sort the first element. So we take the second one and we compare it to the one before it, and if necessary, we swap them. Then we continue to the next element and check if it's in the correct spot. So we iterate through the sorted portion, the left, at this point, if we've sorted 2 of them, the left 2, and we figure out where to put the third one. And we repeat until the array is sorted, and then return that array. All right, so let's implement insertion sort. So I have my snippet ready, and I'm going to define our function called insertion sort. Takes an array. This should be pretty familiar by now. Return that array, and let's call it down here with, what should we call it with? Let's go with 2, 4, oh wait, I'm doing a sorted array. That's not going to work. 2, 1, 9, and 76, and 4. Okay, hardest part of my day out of the way now, picking those numbers. And actually, that's not true. All of this is hard to explain. Okay, so we've got this here, and the first thing we want to do is if we just visualize what we're doing as we go through, rather than starting with the first element, because that can be kind of an edge case. Let's say we've gone through a couple passes, and our array is sorted up until this point. So what do we need to do with 4, for example? Well, what we do, we take 4, and we basically work backwards. We compare it to 76, and we check which one is larger. If 4 is larger, then it stays right where it is, and we're done. But if 4 is less than 76, then what do we do? Well, what we can do is move 76 up to where 4 is. And then we look down to the next one, 9. Where does 4 fit? Well, 9 is still larger, so we move 9 up until where 76 used to be. And then we check 2. Well, 4 is larger, so we put 4 right here, if that makes sense. So we end up with this. So the reason I'm starting from here is because the first easy part is we want to iterate over every item right? That's obvious. All these sorting algorithms so far have involved that. We start with a loop. We start roughly at the beginning, although in this case, we can actually start looping at the first first index rather than 0. And then we look backwards and we figure out where to start or what to do. So let's write our loop for var I equals 1 rather than 0. It's not a problem if we do 0. It's just an extra iteration. And we'll do while I is less than the length, array.length, add 1 to I. Okay, so now what we need to do is first let's make a variable to keep track of the value that we're looking at. So let's say that we're looking at 4. We're going to make a variable called, I don't know, what do we want to call it? Let's go with var current val equals array of I, like that. And now we just want to work backwards. So this is why it's easier, like I said, to think that we're towards the end or the middle of the array rather than at the very beginning, because there is no backwards really to work towards. So let's make another loop to go backwards. So for var j equals, and what should we start it at? Well, we want to start it at 1 less than whatever I is. So if we go back to this example, if this is what we're looking at, if I is right here, so that's 0, 1, 2, 3, 4. If I is 4, we want to start comparing I, or this number, to this number, which is going to be index of I minus 1. So j equals I minus 1 to start. And we're going to make a comparison, which we haven't done yet, and keep going until eventually we find the right spot. So worst case, how many times, for example, if this was 0, how many times do we need to go down? We need j to be 3, 0, 1, 2, 3. We need it to be 2, we need it to be 1, we need it to be 0. And then that's where we would put 0 at index 0. So for that to work, we want to keep going while j is greater than 0, or greater than -1 is one way of doing it, greater than or equal to 0. Which way do I prefer? I don't know. I was going to say I have a preference, but I don't really. Let's do j greater than, let's do greater than or equal to 0. So it's okay if we hit 0 because an index goes to 0, or you could do greater than -1, whichever one. All right. So then we're going to subtract 1 from j every time. So this is just our rough loop skeleton, if you will. So we pick, if I is 4, then we have this loop j that goes from 3 down to 2 to 1 down to 0, and then it stops. So that's just the basic loop, but we don't really want it to just keep looping for no reason. We need to start figuring out where this value goes. Or if we're looking at this example, where does 0 fit in? So what we do, we already have 0, in our case, stored under the variable current val. So whatever I is, we're storing array of I in current val. So we have that over on the side. I'll just keep it over here, the value 0. And my console's not very happy about that. So what happens now is that j is going to start at 76 and move backwards. Well, j itself isn't. J starts at 3 and moves down to 0. What we want to do now is compare current value to array of j. So we could write that out basically like this, array of j, if I can type, array of j, and then we want to compare that to current val. What we want to check is array of j larger than the current value. So if that's the case, if 76 is larger than 0, we want to move 0 down, which what that really means is we're going to move 76 up. So if I show you, let me show you the actual operations. Okay, so first time through, 0's here, we compare current value to 76. 76 is larger. So we actually move 76, we copy it over to here. Remember, we have 0 already saved in a variable, so we don't have to do like a swap with a temporary variable. We already have that temporary variable called current val. So then we move back again to 9, and we compare 9 and 0. 9 is greater than 0 still, so we're going to take 9 and put it there. Now we move down to 2. 2 is greater than 0 still, so we're going to move it to j plus 1. Then we get to 1, which is still greater than 0, so we move it up to here. And then at the very end, if our loop is done, we're going to take whatever this value is and stick it right there. So there's a better way of writing this, and I'll show you what it looks like. It's a little bit confusing to see a for loop like this, but this is one way of doing it. So our loop goes while j is greater than or equal to 0 and array of j is greater than current val. So you may not have seen many for loops written like this, but this is one potential way of doing it instead of a second. You could do a while loop as well, or any sort of conditional check to break out of the loop. But what this reads as, so j starts as I minus 1. We're going to keep going while j is greater than or equal to 0, and array of j is greater than the current value. So if at any point, for example, if instead of 0, this last item was 20, we're going to go through once. Array of j is going to give us 76. That is greater, so we keep looping, and we want to move 76 to here. But then we compare 20 to 9, and all of a sudden, this isn't true anymore. So we're done looping. So now we just put 20 right here. So I know it's kind of confusing when we write it this way, but let me just fill in the rest. So if anytime we're going through this loop, what we're going to be doing is taking a value like this and moving it forward and moving it forward, and then we stop at some point. So to actually move that value forward, it's just array of j plus 1 equals array of j. So why don't I just do a console.log to show what's happening. Console.log array, and actually let's do it in here. So we're not sorting just yet because we're not actually replacing the correct value in. But if I run this, okay, you can see what's happening. So we started with 1 and we look back at 2. Well, 1 needs to go here, so we move 2 forward. So we get 2, 2, 9, 76, 4. We just never added in 1. So to remedy this, after this loop finishes, that means that we found the correct spot for where we need to insert current val. So then here, all we do is insert current val, and it's not array of j. It's array of j plus 1. Because if we walk through this again, let's say that we're starting here, then j is going to start right here. So we check which one's larger. Okay, 76 is larger. So remember, we have 20 saved in a variable. We're going to take 76 and move it here. But j was right here. So next time through, j moves down to here, and we compare 20 and 9. Well, 20 is greater than 9, so we're not going to move 9 forward. But we don't want to swap, we don't want to put 20 right here. We want to put 20 here in this space. So j is this, we want j plus 1. So array of j plus 1 equals, what's it equal? What do we call it? Current val. And now actually we're done. So if we step through now, what happens? Let me clear. Execute. Okay, I'm printing when we move an item forward, which is kind of confusing. So we moved 2 forward, but then on this line right here, we inserted 1 at the beginning. Let's instead do console.log right here. Okay, so where's the start? Here we go. So you can see we go through the first time, and we put 1 where it goes. It goes in front of the 2. Then we're looking at 9. Well, it goes where it is. Then we look at 76. That goes where it is. But then we get to 4, and we need to move 4 all the way to right here. And then we're sorted. So this one's a bit different. I know it's maybe a little harder to understand this code, but step through it. If you do get stuck, I highly encourage you to just write down what I and J are at every point. And just one at a time, walk through. It might take a little bit. Use a shorter array. Definitely, when you're choosing numbers for the array, it helps to choose things that make sense, that like work with your algorithm. If you just pick a bunch of numbers like 2, 2, and 2, or you pick something that's already sorted, it doesn't help that much. So pay attention to that. But walk through it if you need some help. Try and understand what's going on. So insertion sort, as far as its time complexity, it's pretty similar overall to the other two we've seen. It's worst case O of n squared. It's quadratic because as the length of the array grows, we also have to basically make n squared number of comparisons. But if our data is almost all sorted, so if instead we were looking at something like, I don't know, what would work here? Let's say 1, 2, 3, 4, -1, for example. Well, if we look at 2, we immediately find that it's greater. We don't have to do anything. We stop the loop. Then we move to 3. We find that it's greater than 2. We don't need to keep going. We look at 4. We're good. We look at -1. All right, now we have to go through and put it at the beginning. But compare that to totally random unsorted data where we have to continually place something and iterate. then we're looking at a much worse time. Or actually, what's the worst possible scenario? Something like this, where you start, we get to 3, we have to swap it to here. Then we get to 2, we have to swap it to the beginning. Then we get to 1, and we have to swap it to the beginning again. That's the worst case for insertion sort. But if your data is nearly sorted, you're good. Now, another interesting thing that insertion sort is good at, if your data, there's something called an online algorithm, which is an algorithm that can work as data is coming in, as it receives new data. It doesn't have to have the entire array at once. So for example, let's say that we have some code where people are submitting numbers to us online, live. We're getting them and we want to sort them in. Don't ask why, but let's say we wanted to. With insertion sort, because the way that it works, that we're keeping one side of the array sorted and we're inserting items one at a time, it doesn't matter what the number is that comes in, we can place it where it needs to go. So that's one strength. If you're looking for a sorting algorithm that works in that way, which I probably isn't going to come up, but it is worth knowing that because of how insertion sort works, because we keep one side of it sorted and we insert things in the appropriate place, because of that, it works well in a situation where data is coming in live or streaming and you need to insert it at a moment's notice. Okay, so those are the 3 elementary sorting algorithms. In the next video, we'll just wrap up talking about their time complexity and space complexity, and then also do a quick recap of what we learned.